Now, the key to understanding chemical equilibrium is to understand the concept of yield, which is the efficiency of the reaction. And yield is defined as the measure of the extent of a reaction. In other words, how well it goes, generally measured by comparing the amount of product against the amount of product that is possible. So your percentage yield, let's say you could get 30 grams of product, but you only get 23 grams of product, then it's going to be 23 out of 30, and you would work out a percentage yield. So the important thing is to realize it's how well the reaction goes forward. I'm going to look at a reaction in a little bit of detail now. This process is known as the Haber process, and it is a process where nitrogen and hydrogen are pumped into a container, and then they mix together, but they're not going to react with each other unless you put them in the reactor vessel, and then you get some ammonia coming out. You will notice that the percentage yield gets lower and lower as you increase the temperature, and as you increase the pressure, however, the percentage yield gets higher and higher, and you get more ammonia coming out. Whatever isn't used goes back into the system and goes around again. Inside the reactor there is a catalyst, and that helps the reactor to work better. Notice, as I increase the temperature, less and less yield comes out, even though it's going faster. And as I increase the pressure, I am going to increase the yield of the reaction. So I'm going to get a maximum yield at a low temperature and a high pressure for this particular reaction. So this reaction is called the Haber process, named after Fritz Haber, who happened to have also been the man who developed the gas chambers, but that's another story. And what happens is you've got hydrogen and nitrogen, they get together to form ammonia. And we balance that equation in the following way. Let's explore the criteria of that. So here's that balanced equation that we've just described, and we've got a delta H value that is less than 0. That tells me this is an exothermic reaction. Now, you need to consider how the factors of concentration, temperature, and pressure affect various reactions. If I were to put more nitrogen into the container, the system would attempt to use up that nitrogen by making the forward reaction go faster. Remember, there is a forward reaction and a reverse reaction going here. But because I have added more concentration of reactant, I will favor the forward reaction. The same is true if I pumped more hydrogen into the container, I would favor the forward reaction. You'll remember from that animation they were continually pumping nitrogen and hydrogen into the reactor vessel in order to try and keep their concentrations as high as possible in order to make as much ammonia as possible. So an increase in concentration, we all know an increase in concentration makes the rate go faster, which is great, but that doesn't mean the yield gets better. We need to see what happens with the yield. An increase in concentration of any reactant will cause an increase in the reaction rate of the forward reaction. That is written from left to right. The other thing I can do to get the forward reaction to go faster is to keep taking product out. And you'll remember from that system that the product was going out at the bottom all the time. So they were removing ammonia all the time. The way they do that is by dissolving it in water, because ammonia is highly soluble in water. So they spray water over it all the time and the ammonia keeps dissolving. So increasing the concentration of, if the ammonia is removed from the reaction vessel, the forward reaction is favored. Let's look at some of the other conditions. So over here, if I look at the balanced equation, I've got 1 mole reacts with 3 moles to produce 2 moles. Altogether on the reactant side, I have got 4 gas moles. I'm only interested in the gas moles. On this side, I have got 2 gas moles. Gas, gas, and gas. So, if I were to put pressure onto the system would try to make itself smaller. 4 is a big number compared to 2, which is a small number. Now, gases occupy space based on how many moles there are. Because of the big spaces between the particles, the actual size of the particle makes no difference. It's how much space there is in between and how many moles there are. So there are 2 moles of gas on the right, and there are 4 moles of gas on the left. So if I put more pressure, if I increase pressure, then I'm going to squash everything together. It's going to try and make itself small. So when the volume of the container decreases, according to Le Chatelier, the reaction will minimize that change in pressure by favoring the forward reaction in order to have the least number of moles at least. If I went the other way, if I, let's say, released the pressure, lowered the pressure, it would favor the reverse reaction, which would occupy more space because of the 4 moles. Let's look at temperature. We can see, and we said at the beginning, that this was an exothermic reaction. So it gets hot. If I make this reaction colder, it will try to make itself hotter. So colder always favors the exothermic. And that means that in this case, the forward reaction would be favored. If I made it hotter, I actually, although I speed up the rate, I will decrease the yield because the system will try to go towards the endothermic reaction if I make it hotter. So hot always favors endo. And in this case, that would be the reverse reaction. So an increase of temperature always increases the rate of both the reactions. So you've got to kind of get a balance because you don't want the reaction to go slowly, but you do want a decent yield. Delta H refers to the forward reaction. It is negative, and that means the forward reaction is exothermic. So in order to favor the forward reaction, I need to cool the system down so that the system will relieve that stress by trying to get hotter. Catalysts increase the rate of both the forward and the reverse reactions. They do not affect the equilibrium, but they do allow for the equilibrium to be reached more quickly. So they present an advantage in that way. But the equilibrium position does not change. So how are we going to make this stuff really, really well? What are the optimal conditions for making ammonia via the Haber process? So you will use a catalyst, and it's an iron oxide catalyst, so it's an Fe2O3 catalyst, but that's not a big story now. You will need to know it eventually. Take that catalyst, and when the equilibrium is reached, you drop the temperature down to 450 degrees centigrade. And you might say, well, 450 isn't very cold. By industrial standards, it is quite cold. And don't forget, you still want a decent rate. So when we're looking for the optimal conditions, we're looking at a balance between rate and equilibrium. So this will be a low temperature in terms of industry. We're going to put as much nitrogen and hydrogen in, and we're going to have as little ammonia as possible. We're going to move it by dissolving it in water all the time. And then we're going to put lots of pressure on the system by reducing the volume, and all of that extra pressure favors the rate as well. So you'll have a high rate and a high yield. Why? Because there were only, it was 4 moles of gas to 2 moles of gas. So more pressure meant that it will go to the side with the least number, the smallest space that will be occupied, which is the 2 moles of gas. Here are some general things to always remember. So generally speaking, when I increase the reactant concentration, it will use up more reagent. Decreasing reagent concentration, it's going to go to form more reagent. In other words, will favor the reverse. The same is true of product. Increase product, it will favor reactant. Decrease product, like we did with ammonia, we are going to favor the forward reaction. If I increase pressure, it will always go to the least number of gas moles. A decrease in pressure will always go to the most number of gas moles. An increase in temperature favors endothermic. Decrease in temperature favors exothermic. And although a catalyst speeds up the rate of the forward and the reverse reaction, the equilibrium does not change. These are some common reactions that they like to ask in equilibrium. So I just wanted to put them into your notes so that when you see them, you go, oh yeah, that's that familiar reaction over there. As you can see, the Haber process is one of them. This is part of a process known as the contact process, and there's also some reactions that are part of the something called the Oswald process, which we'll look in more detail. But we often look at something called the general equilibrium reaction, which is A plus B gives me C plus D, which gives me A plus B, which gives me C plus D. And if I look at that, if I'd write it like that, these are considered to be the reactants, and these are considered to be the products. We're going to use this reaction in the next section when we start looking at something called the equilibrium constant.